The universe, without a doubt, broadened, enabling endlessly more expansion after this period. It endured growth, although at a slower pace, eventually transforming into the universe we focus on recently. That is the inflationary theory of the ancient infinite effect, the most widely recognized and generally accepted hypothesis of how the universe began. However, for some physicists, this leading hypothesis no longer exactly paints the picture of our universe. They propose that the universe existed before the Big Bang, stretching infinitely into the past as well as into the future. Even as the universe is expanding today, it was contracting before the Big Bang. In this view, the Big Bang isn't exactly a bang, but rather a leap, a moment when the contracting universe reversed course and began to expand once more. According to this theory, the universe may undergo continuous cycles of expansion and contraction, potentially avoiding a complete collapse in the distant future. Some physicists even propose that this process might be infinite. This contrasts sharply with the standard cosmological view, which holds that all matter originated from a massive explosion. This theory also confronts the concept that something cannot emerge from nothing. Adding to the debate, the James Webb Telescope has made surprising discoveries that challenge the idea of the Big Bang as the definitive beginning of the universe. These revelations raise the question: if the Big Bang wasn't the start of the universe, then what was? Should the universe have eventually begun with an explosion or something else entirely? The notion that the universe had a beginning, or a night with no yesterday, first emerged with Georges Lemaitre in 1927. However, it remains an imperfect model for explaining the universe's origins. The history leading up to the hot Big Bang that describes our current universe has little to do with what may have come before. While many experts in cosmology live with the belief that the Big Bang marks the earliest point of everything, the Big Bang does not necessarily signify the birth of life as we know it today. In fact, there is substantial evidence pointing to a non-specific beginning of our universe. We never reached these conclusions based on direct observations or incredibly high temperatures. The universe is best described through an inflationary period that occurred before the Big Bang. The Big Bang is the final outcome of what transpired during the climax of cosmic evolution. During this evolution, the universe was largely empty. No debris, no photons, just a void. Space itself was filled with an immense amount of energy everywhere, which over time transformed, spreading rapidly in a precise and uniform manner as the universe slowed down. These changes led to massive expansions while new-scale fluctuations were created and amplified. This superposition of uncertainties across different scales is a defining feature of cosmic development. If you lived in an expanding universe, you might encounter regions where development ceased, or the space between you and them slowed down indefinitely. In short, you could try to observe what happens closer to the beginning of a large impact before that region faded from view. This scenario involves a small region, likely no larger than a human-sized hamster ball, although potentially much larger. The energy in that region then transforms into matter and radiation. This transformation occurs rapidly, taking shape quickly but not instantaneously, as the energy within itself converts into particles and photons. The temperature quickly rises from just above absolute zero to around 20 Kelvin within a very short period. Due to the immense energy released, everything moves at nearly the speed of light. All particles behave like radiation, whether they are massless or massive. This transformation is called reheating, marking the end of cosmic inflation and the beginning of what we refer to as the new Big Bang. As inflation continues, you will witness a dramatic shift from previous conditions when the current Big Bang begins. The expanding universe slows down after the initial moment of inflation. Before the Big Bang, you might experience inflation pushing up against adjacent regions where inflation ends, filling up with antimatter and radiation, and gradually creating new structures. These regions will become part of the expanding neighborhood, serving as a standard connection within spacetime. In the inflationary picture, distant regions where inflation continues will fade from each other's view. Consequently, the inflation rate changes, with a slight chance that any universes with separate warm Big Bangs will ever merge. The region where we reside gets rather fortunate as inflation comes to an end. The energy typical for space itself transforms into a highly dense and nearly uniform distribution of particles, with only minor deviations. These fluctuations are the result of quantum changes that existed and were amplified across the universe during inflation. These quantum fluctuations initially created overdense regions, while negative energy fluctuations transformed into underdense regions, serving as the seeds of massive structures. We cannot see these density fluctuations today, as they occurred during the universe's early development. There are no observable imprints from that early period after passing through further interactions, although we can extrapolate back to understand the initial density instabilities. These fluctuations align with the story of cosmic inflation, where temperature instabilities are engraved in the cosmic microwave background, CMB, providing evidence of how the Big Bang started. However, there are still anomalies, most notably the CMB and our modern version of cosmology suggest that we are missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe is not behaving as expected. The light from the CMB is being lensed through our local environment, meaning that the light acts like a giant lens, bending and altering its intensity. The amount of this lensing is not always consistent with our current model, indicating a need for further investigation. Additionally, the 2 hemispheres of the CMB sky exhibit asymmetry, with one hemisphere showing higher average temperatures than expected. This asymmetry challenges the assumption of uniformity in the universe's earliest stages. Third, the value of the Hubble constant, which describes the rate at which the universe is expanding, varies depending on whether it is measured from the cosmic microwave background, CMB, or from nearby stars. All these anomalies suggest that we are missing something fundamental in our understanding of the universe. One proposed solution comes from loop quantum cosmology, which stems from loop quantum gravity. In this framework, there is a minimum size of space, on the order of the Planck scale, about 1.0*10 to the power of -35 meters. This approach suggests that the Big Bang couldn't have occurred in a universe governed by this principle. Instead, the universe may never have reached an incredibly small, dense state near the Big Bang. In loop quantum cosmology, when the universe becomes very small, quantum corrections introduce a repulsive force, causing a bounce rather than a singularity. This suggests that our universe could have originated from a previous universe that contracted and then expanded again, like a phoenix rising from the ashes. While the idea of a big bounce isn't entirely new, loop quantum cosmology provides a mathematical framework to support this cyclic model. This cyclical time model offers compelling evidence of the universe's origin, further validating the possibility of a bounce. Traditional loop quantum cosmology provides a persuasive and accessible route to the modern Big Bang theory, potentially resolving some long-standing anomalies in cosmology and offering insights into the origins of the universe. This theory also highlights the importance of remaining open to new ideas and perspectives as we delve deeper into the mysteries of the universe. As we explore the theories that attempt to explain its origins and evolution, we encounter a rich tapestry of ideas and discoveries that challenge our understanding of the universe's beginnings. From the early details of the Big Bang theory to contemporary advances in cosmology and quantum physics, the quest to unravel the secrets of the universe has been a journey marked by profound insights and ongoing mysteries. The Big Bang theory, which emerged in the early 20th century, represents a pivotal moment in our understanding of the universe's origin. It posits that the universe began as a singular point of infinite density and temperature about 13.8 billion years ago. This primordial state rapidly expanded in an event known as cosmic inflation, where space itself expanded faster than the speed of light. The inflationary period lasted for an imperceptibly brief moment, but its effects set the stage for the subsequent evolution of the universe. During inflation, quantum fluctuations in the fabric of spacetime were amplified to cosmic scales, fostering the development of structures we observe today, such as galaxies and clusters of galaxies. These fluctuations left an imprint on the cosmic microwave background, CMB, radiation, which is now studied to understand the universe's early conditions. The discovery of the CMB in 1964 provided definitive evidence for the Big Bang theory, as it offered a snapshot of the universe when it was only 380,000 years old, a mere blink of an eye compared to its current age. Following the inflationary epoch, the universe entered a phase dominated by the interaction of elementary particles and radiation. This period, known as the Hot Big Bang, saw the universe cool and expand further, allowing protons and neutrons to form within the first few minutes. These nucleons eventually combined to form the first atomic nuclei in a process known as Big Bang nucleosynthesis, which laid the foundation for the universe's chemical composition. As the universe continued to expand and cool, photons decoupled from matter, creating the cosmic microwave background radiation. This faint glow permeates the universe and provides essential insights into its early history. Measurements of the CMB have revealed subtle temperature fluctuations, corresponding to density variations in the early universe. These fluctuations served as the seeds from which galaxies and larger cosmic structures emerged through gravitational attraction over billions of years. While the Big Bang theory has provided a robust framework for understanding the universe's development and early evolution, it also raises important questions about what came before and what lies beyond. The concept of cosmic inflation, for example, suggests that our observable universe is just a tiny patch of a much larger universe, possibly one among many in a multiverse. Inflationary cosmology proposes that rapid exponential expansion occurred not just once, but possibly multiple times, giving rise to a collection of universes with different